And now we try to evaluate the bandwidth of angle modulated signals. We start with the sinusoidal modulation or sinusoidally modulated waves. And we look at figure 4, 2, and table B1. Table B1 is the one that I have shown you right here. And table 4.1, 4.2 is the one that is right here. So what we observe from these two tables is that the bandwidth of agomodulated signal with the sinusoidal modulation depends on beta and omega m. So as you can see, we are having two parameters. One of them is beta, the other one is omega m. So the higher the omega m, the wider the this spectrum is going to be. And of course, the higher the beta, the value of beta, the more spectral components we are going to observe. So what we see from that diagram is that it can be shown that 90%, 98% of the normalized total power is contained in the bandwidth, whereby the bandwidth is going to be defined as 2 beta plus 1 of omega m. And therefore, we are saying that for a narrow band, when beta is far much less than 1 and we consider 0.2 to satisfy that condition, then we say that the bandwidth is going to be estimated to be equals to 2 omega m, because we have said that the bandwidth is given by 2 beta plus 1 of omega m. So when this is far much less than 1, then we can simply consider this to be approaching 0. And therefore, when it approaches 0, then we can say that bandwidth can be approximated to be equal to 2 omega m. And therefore, for an arbitrary modulation, B, that is not purely sinusoidal, we can also define a similar term that allows us to estimate how much bandwidth the spectral how much the bandwidth of the spectral components occupies. So for an angle modulated signal with an arbitrary modulating signal MT that is band limited to the omega m radians per second, so then we can define the deviation ratio D as the maximum frequency deviation divided by the bandwidth of the message signal MT, which is omega m. And we say that the deviation ratio D plays the same role for an arbitrary modulation as the modulation index beta. So we can replace beta with D and omega m with omega capital M in equation 425 that we saw earlier, which will now allow us to define the bandwidth of a narrow band wave that we had said earlier to be given by this equation. And therefore, when you replace beta with this is bandwidth. When you replace, sometimes you can write it like that one, you can write omega b. That is the proper way of writing the bandwidth. Then we can say that the bandwidth of arbitrary modulation will be expressed by 2 d plus 1 of omega capital M. And that allows us to use the different term, which is the deviation ratio D, instead of the modulation index beta that is only defined for sinusoidal modulation. So we say that this definition in equation 427 is what constitutes or what defines the Carson's rule. And we say that if D or the deviation ratio is far much less than 1, then the bandwidth is approximately what we have seen already here. It should be approximately equal to 2 omega m, and the signal is said to be narrowband agomodulated signal. And if D is far much bigger than 1, then we say that the bandwidth is approximately, we had the definition for the bandwidth as 2D plus 1 of omega m. So when d is far much bigger than 1, this will become insignificant, and therefore you're saying the bandwidth will be approximately equal to 2d omega m. So if I think that is something we have already said. The bandwidth is approximately equal to 2d omega m, which is equal to 2 maximum angular frequency change that we had already said earlier, which is twice the frequency, the peak frequency deviation. And therefore, such a signal is called wideband modulated signal. So we have two definitions now for wideband modulation. One that is defined for a sinusoidal wave with D, and the one that is defined for non-sinusoidal, that is arbitrary. Sorry, the one that is defined for non-sinusoidal, that is arbitrary, is the one that is expressed in terms of D. And we have said that the bandwidth is given by 2d omega w, and for d bigger, far much bigger than 1, we have a wideband modulated signal. And the other way we defined it is that when we had beta for sinusoidal modulation, and we say that for beta is far much bigger than 1, then again we also refer to that as a wideband modulated signal. And on the converse, we can also define the narrowband, where we have beta far much less than 1, that is narrowband modulated wave. And similarly, when d, or the division ratio, is far much less than 1, again we are able to define the narrowband modulated signal.